Okay, so let's continue our discussion. So we have looked at what are min terms, what are max terms, then canonical SOP form, canonical POS form. Right, so let's look at the next topic, which is from canonical SOP form, how can we go to canonical POS form without using the truth table? Okay, so let me call it as canonical SOP, sum of the product. From there, or you can go in the reverse way also, canonical POS. So how can we if we know one form, then how can we write the other form? For example, you are given something like this: f of abc is equal to m1 m2 m4 m5. f of abc is equal to m1 m2 m4 m5. Now how can we convert this into the POS form? And the POS form we got is m0, then m3, m6, m7. So how can we get this? So that is the consideration now. And one thing you can notice is that all the min terms which were absent, the corresponding max terms are present in the other form. In other way, they are like complementary related. If one is present, the other is absent there. Okay, whatever is present here, whatever min terms is present here, the corresponding min terms are absent there, and whatever is not present here, they are present there. Okay, so that you can just see by observation. But formally, how do we show that this is the case? Okay, so in order to see this, we will use what is called as the DeMorgans Theorem. Okay, so first what we do is that we take complement of f complement a b c. So that means you start with your SOP form, the complement. Now by DeMorgans theorem, we know that the complement of sum of many terms is basically given by m1 dot m2 dot then m4 complement m5 complement. So this is basically the statement of DeMorgans theorem. We proved it for two variables, but same thing can be proven for multiple variables. It is not tedious also. All you need to do is basically you take m2 plus m4 plus m5 as just one, treat it as one variable, and then you write m1 dash dot then m2 plus m4 plus m5 the whole dash, right? So that way, okay, so if you want to see this proof for multiple variable, you start with you treat this as one variable, okay, and then when you take complement, so since you already know the proof for two variables, you can write like this. Right, and then what you do is now you treat this as another variable, and then this can be written as m2 dash dot m4 plus m5 all dash. Okay. So which you can continue. Now you can apply DeMorgans here. So then dot you apply DeMorgans theorem one more time for M4 and M5, you will get basically M4 dash dot M5 dash. Then we know that associativity is basically a theorem that we have proven. So how do we associate whether this first or this? Doesn't mean everything is same. So you can write it as so I applied DeMorgans theorem step by step, and then used the associative property. Okay, so this is associative. So I get it. So I can just show. So DeMorgans theorem is valid for multiple input. I mean more than 2 inputs also. Okay. Now what is M1, M2, M3? So where M1 is what? M1 is basically A bar B, A bar dot B dot C bar. Then M2 is what? M2 is basically M1 is basically A bar B bar C. That is M1, and M2 is basically A bar dot B C bar. So wherever 0 comes in the combination, you put bar. Whatever is directly coming, you put direct variable. And then we have M4. M4 is A dot B bar dot C bar. Then M5, that is the last one. I have A dot B bar dot C. Alright, so these are the terms which are present. So now what I need is the complement of it. Okay, so F complement A, B, C is basically equal to A bar dot B bar dot C complement dot A bar dot B, A bar dot B C bar complement dot. So bar and complement, they are basically meaning the same thing. I am using it interchangeably. A, B, C complement dot A, B, A bar C complement. Okay. Now if I apply DeMorgans theorem once again, what will I get? I get A plus B plus C bar. Then dot A plus B bar plus C dot A bar plus B plus C. Again I am using DeMorgans theorem into A bar plus B plus C bar. Okay, so this is what I get as for F dash. So this is actually in POS form, but it is actually giving F dash. So this is what? This is basically M1, then M2, then M4, and then 5. Okay, so the complement is equal to we have basically made the. So what did we do? So what we did is basically we started with F, okay, which is M1 M2, M1 plus M2 plus M4 plus M5, and then if you take the complement of that function, that can be written in POS form as same, right? So M1, M2, M4, M5. Only thing is that the same max term is actually present, where whichever min term was present, the corresponding max term is now present. Okay, so I hope you are able to get what I am trying to do. So let me just write the truth table once again, but this time with the F complement also. Okay, so A, B, C, and then you have F, and then F dash. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Okay, so what are the min terms that are present? There was a 1 here, and then there was a 1 here, and this was a 1, and this was a 1. All other 4 cases it is 0. So when I take complement, what I mean is basically wherever it was 0, it will come 1. Wherever it was 1, it becomes 0. That is F complement. Right? Now, so we are basically looking, if you want the canonical SOP form, we look at this once. Okay, and if you want the canonical POS form, we have to look at these zeros in the F. Okay, now so what did we show? So what did we show is basically, if we start with the min terms of F, and then if we took the complement, we will basically get an expression which is in max term form, where all the zeros which are in F complement will be denoted by using max term. Now, had if we started with the min terms of F complement, then we would have got the max terms corresponding to F, right? Because F complement is basically F complement is basically F. F complement is equal to F. So if we had started with min terms of F dash, so which is basically this, and then if we have worked out the same thing, then we, wherever F dash is 1, the corresponding min terms would have come out, right? Just like here. So that's what we need to do. So in order to convert, so this will go back. So in order to convert the given Boolean expression into POS form, what we need to do is basically start with the minterms of the complement. Start with the minterms of the complement and then apply one more complement and do this DeMorgans theorem, and you will get the max term. Okay. So if you start with the minterms, so f dash is what? In minterms, f dash is basically m0 plus m0, sorry, not m0, m1. Yeah, I mean, if you look at f dash in minterms is all the cases where you have 1. So you start here, this is 1, this is 1, this is 1, and this is 1. So this is m0, and then you have basically 0, 1, 2, 3, m3. Use this color, m3, and then it is 1 for m6 and m7. Okay, so you start with the minterm representation of f dash, and then what we do, we take the complement of the complement, which is basically f, and this you will get it as m0 by applying DeMorgans theorem. By following the same steps, you will get it as m3, then m6, m7. So that is basically the representation of f as POS form. So this is our product of the sum form. Canonical, I should say canonical. Okay, I hope this is clear now how to convert. The step is basically, first step is basically go to f dash and represent f dash in terms of minterms. Okay, if f is given as minterms, f dash minterm is basically just the complement. Okay, whatever is not present, that is basically the, because 1 will become 0, 0 become 1. So whichever cases become 1, that is what we need to write. So whatever minterms which were absent, that will become present. So that is so what was given earlier is f. So f was basically m1 plus m2 plus m4 plus m5. Okay, so from this we go to f dash. So whatever is present will be absent, and remaining one you have to take, and then you apply one more complement and write all the expression by using DeMorgans theorem, and that will give you m0 dot, capital M0 dot, m3 dot, m6 dot, m7, which is the canonical POS form. Alright, so this is the way. You can go in the opposite direction also, same procedure. If so let me show you one more example. It is exactly the same procedure. Okay, so f, example say 2, f is given a, b, c, let's say d also, and it is given as say 1, 2, 5, 6, 10, 11, 13, 14. This is what is given. Okay, so if you want, let's put more terms, 15 also. Okay, so this f is given, and so f dash of a, b, c, d is basically sigma, whatever is not there, 0. So even a small m I dropped, because sigma is there, means it is, this all has to be small m. Okay, so you have to this is even more concise representation. Okay, 0, then 1 is there, 2 is there, 3 is not there, 4 is not there, 5, 6, 7 is not there, 8 is not there, 9 is not there, 10, 11, 12 is not there, 13, 14, 15. Okay, that's all. So this is what we have as for f dash, which if I now expand and write, this is basically a bar dot b bar dot c bar plus a bar dot b dot c plus a, sorry, I have to use 4 variables, so let me do that. So dot c dot d bar plus, then 3 is basically a bar, b bar, then c d, that is 3, then 4 is basically a bar, b, c bar, d bar, then 7 is basically a bar, b, c, d, 8 is basically a, b bar, c bar, d bar, then 9, so 9 let me write here, a, b bar, c, d bar, sorry, a, b bar, c bar, d, plus 12, a, b, a, b, c bar, d bar. Okay, so these are the 7 terms which are part of min terms, which are part of, so this is basically I am writing m0, m3, m4, m7, and then plus m8, m9, m12. Okay, so these are the 7 terms. Now what I am trying to do is basically taking the complement of the complement, so which is basically f, and apply the DeMorgans theorem. So what will happen, the entire thing is complemented and individual terms, so we will have a bar, let me write a bar, b bar, c bar, d bar, the whole complement, dot a bar, b bar, c, d, the whole complement, a, c bar, d bar, the whole complement, dot a, b, c, d, whole complement, dot a, b bar, c bar, d bar, whole complement, dot a, b bar, c bar, d, the whole complement, a, b, c bar, d bar, whole complement. So individual terms now need to be complemented. So then what you will get? You will get basically a plus b plus c plus d dot a plus b plus c bar plus d bar. So 2 times we are applying DeMorgans theorem. Okay, in step this here also we applied from here to here, and then that is complement of this we applied 1 time, and then in the further step individual terms we are applying DeMorgans theorem. So a plus b bar plus c plus d, then a plus b bar plus c bar plus d bar dot, then a bar plus b plus c plus d dot a bar plus b plus c plus d bar dot a bar plus b bar plus c plus d. Okay, so now we got the final POS form, which is basically product of so which are the terms which are present now? So the first term is which one? A plus b plus c, that is your m0. Okay, so you can just write it as 0 also, because pi means it is product. Then next one is which one? This is 3, right? And the next one is this one is 4. Next one is 7. Next one is 8. Next one is 9, and this one is 12. Okay, so which is basically M0, M3, M4, M7, M8, M12. Okay, so once you know this, you don't need to repeat this procedure. So once you take f dash by listing out all the possibilities which were not here, then now you know the pattern, how it is coming out. Basically whatever is in the f dash in min-term representation, all those terms will come as max terms when you take one more complement. Okay, but if you are asked to do a formal proof, so then you have to do all this algebra. Okay, so now next thing we would like to look at is basically, is it the only way to represent? Is there any alternate way of representing the given Boolean function? It turns out that yes, there are more ways you can represent the Boolean function. Okay, what we can do is basically simplification of the Boolean expression. That means we can write down the simpler expression compared to what we wrote down earlier. So let's go back to our earlier example itself, f of a, b, c. We had basically okay, let me just check out this one. Okay, this example let us take again, that is m1, m2, m4, m5. Okay, so this is what is given. So if I write this a bar b bar c plus a bar b c bar plus a b bar c bar plus a b bar c. Okay, so this is what is given as the Boolean expression. Now we have learned some of the Boolean algebra theorems and postulates, etc. We can use them to try and find out more simplified expressions if it is possible. Okay, so first thing that we need to, in order for simplification, we have to group these terms. For example, just as an example, if you look at these two terms, the last two terms, you can see that a b bar is there in both, and then you have c and c bar. So that looks like we can apply a distributive property, right? We can apply a distributive property, and then once you apply the distributive property, then we can see whether we can get a more simplified expression. So that is one thing. Any other such things? Let's see whether you compare two terms, if only one particular literal is changing, otherwise everything is same. So check for other possibilities. Let's see. I don't directly see any other possibilities. Okay, let's do this. A bar B bar C plus A bar B C bar. So here I am saying A bar B bar I can take common and dot it with C bar plus C. So this is the distributive property, right? So if I distribute it, I will get back. Now secondly, what is this? From Boolean algebra, this is equal to 1, and this property is basically complement. Right, this is equal to 1 by complement. I mean, this is a definition of complement. Okay, I mean, there are two parts to it. One part is that C plus C bar equal to 1, other is basically C dot C bar equal to 0. So if you apply that and then apply identity operation, you can get identity property. You will get plus A. Now, so this is also a valid way of writing down the given Boolean function. Okay. Now this also require only two levels of for implementing this. We only require two levels. One is basically creating the product, and but now you see that the product term is smaller. It has only two variables, so the number of input that is required by the gate is now reduced. So this, in a way, this is more effective implementation, because it requires it requires lesser hardware in terms of the number of inputs that are needed for creating the product terms. So that is an advantage if you try to implement with this expression rather than the initial expression. And this expression is like, another thing is like the number of input to the OR gate is also only 3. Earlier it was 4, but now it is 3, and the number of input to one of the AND gate is also 2, not 3. So this expression is called standard. Standard SOP form. Okay, this is called standard SOP form because this is also SOP form, right? Sum of the product terms, and it can be implemented in two levels, but it has in standard SOP form, unlike the canonical SOP form, you don't need all the literals to be present. Okay, you can have some of the products with lesser number of literals. Okay, here C is absent or C bar is absent, so that is also acceptable. Okay, in other words, we are saying is that if you say this term is present, then it doesn't depend upon whether C or C bar. That's what physically it means. Now you can represent this. 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 You can represent this in so many other ways also. Like for example, I can take this a bar common out of here. So if I take the a bar common, this is also distributive property. Okay, let me go back to the blue color. If I take the a bar common and then b bar dot c plus b c bar and then plus a. Now if you want to implement this expression, so this is not two level, right? This require more than two levels. First I need to create this product term, then a sum term, then another product term, then another sum term. Okay, so if you look at the implementation of this, suppose b bar is available and c is available. So you create an AND gate, and then I have b also available, c bar is also available. You use another AND gate, and then the result of that AND gate I give to OR gate, and then I have another term which is a bar. I need to take the AND gate, that, and then I have a and b bar. From that I use another AND gate here, and then this has to give to OR gate. Okay, so this is my f. Okay, and you see the number of levels here in the implementation. So this is level 1, then you have another OR gate, level 2, this is level 3, level 4. Okay, so this one is non-standard. SOP Form, non-standard. Okay, so here we can't implement this expression with just two levels. We have more than two levels. So in this particular case, there is 4 levels that are required. And what is the problem with the non-standard implementation is because the problem is basically you need more time to get the output, because each of the gate would introduce some propagation delay. Okay, so for example, this AND gate, 2 input AND gate has a propagation delay, let's say tau 1, and then this 2 input OR gate has another propagation delay, say tau 2, and then again tau 1, and then tau 2. So the total propagation delay, that means after applying the input, for level 1 you have tau 1, level 2 you have tau 2, level 3 you have again tau 1, though you could compute this one earlier, but here you have to wait till the output of this OR gate to come, which will come after T1, then T2, T1 plus T2 only the input will reach, then it will take again another tau 1 to get the output, and once it is available only then final computation. So here it is 2 times tau 1 plus tau 2. So if the AND gate has a delay of tau 1 and 2 input AND gate, and the OR gate also has a delay of tau 2, then 2 into tau 1 plus tau 2 is the total delay of this circuit to generate the function after giving the input. Okay, in direct or complement form, if we assume it is available, then this much delay is required. Whereas if you go to the standard implementation, so that is here, this one, you can see that here the AND gate will have tau 1 and OR gate will have tau 2. So the delay here is propagation delay is equal to tau 1 plus tau 2, not 2 into tau 1 plus tau 2. But the price that we need to pay is that the number of input. So here we require 3 input AND gate and 3 input OR gate. Okay, so that is a bigger circuit which has bigger area requirement in building that circuit in the electronic chip. But as far as the time consumption for creating the output is concerned, the standard SOP is faster. Okay, standard SOP is faster compared to non-standard. But here non-standard, if you look at, all gates are 2 input gates. Okay, but you need multiple number of them. Okay, whereas in standard SOP you have 3 AND gate, 3 AND gate and 1 OR gate. That's all. And all the AND gate will compute the product term parallelly, and then the OR gate will compute it using the result produced by the AND gate. Okay, so that is why only tau 1 plus tau 2. Okay, so standard and non-standard is another classification. Where in standard you have all in SOP form or POS form. So there is standard POS form also, which I did not discuss, but you can think about it in the similar manner. And non-standard form is like this. Okay, now one more thing I want to, so here we talked about going from canonical to standard SOP form. So in canonical form we had all the literals present, then we simplified it by using the results of Boolean algebra in order to get so we can do more examples like this. The book that I have given, you can check. There are more examples for given for simplifying the Boolean expression. Now the other way, like you would like to see, is like how can we go in the reverse order. That is, if a standard form is given, how do we arrive at the canonical form? Okay, the opposite way of going. So opposite of like simplification. So how can we do this? So let us take some example. Let me take some example from the book itself. Okay. Question. So this is an example which I am taking from the book. Find the canonical SOP form of the Boolean function f of x comma y comma z is equal to x dot y plus x dash dot z. So this is definitely not in canonical SOP form, but it is in a standard SOP form. There are only 2 levels, but in each there are only 2 terms, but each term does not have all the literals present, so we need to bring in. Okay, so given f of x comma y comma z is equal to x dot y plus x dash dot z. Alright, so this is a very simplified expression, but in canonical form we need to have all the terms present. So if you look at the first term, we don't have z there. So what we do is basically multiply it with or dot it with 1 and then write 1 as z plus z dash. Similarly, if you look at the second term, you can see that here also you can multiply it with 1 and then I can write that 1 as y plus y bar. So what are the property I have used? Multiplication with 1, that is identity element. Okay, identity element. 1 is the identity element, and then definition of complement. These two are what I used. Okay, but I have not explicitly shown here. You can say that this is multiplied with 1 and this is multiplied with 1, and then 1 is written like this. Alright, so maybe I should write it with a different color. Now all you need to do is x dot z, then x dot y dot z dash plus x dash dot y dot z plus x dash dot y dash dot z. Okay, so here I have just used distributive property and then commutative property also, because I have just interchanged the order. Y was at the last position, I interchanged it with z. So two properties I have used, distributive and commutative. Okay, so now I have all the minterm representation here. So let me just so this is, first one is basically M7, next one is M6, next one is basically M3, and the last one is basically M1. So you can write it as 1, 3, 6, 7. Okay, so this is the canonical SOP form. All the minterms we find out by using this. All right. Now another example. Let us see example 2. Given f of x comma z is equal to x plus y dot x dash plus z. This is another example. So this is similar. This is basically the dual of the previous problem, but how do we do this? So question is, find the canonical POS form. Okay, so that's the question. So is basically, you can write it as x plus y plus 0 dot x dash plus 0 plus z. So I introduce 0, and this is basically identity element of plus operation, so I can add 0 in any term here. Now what will I do? I replace the 0 with z dot z bar y dot y dot. So which is this? This is basically the complement, the definition of complement. Then what else? I distribute. So x plus y, you treat it together and distribute it with this So similarly here also, so if you want, you can apply commutative property as well as distribution to bring things in order. So that's the canonical POS form. So here I have used again distributive property. And then commutative. Now what is this? This is your M0 and then this is your M1. You have here basically M4 and M6. So you can write it as pi 0, 1, 4, 6. Okay, I hope I am correct. So this is the way we can go. So if you want to basically go from the standard form to the POS form, you either in here for POS you introduce 0 and then use distributive property and expand it like this. And yeah, so that's it. Yeah, so I would like to stop here, and if you have any queries you can ask. We have 4 minutes left. If you have any queries you can ask. Any doubts, any questions? So from canonical form to standard form we go by simplification approach. The opposite way to go, we use we insert zeros and ones, and then we try to bring the literal which is absent in the each product term or sum term. So x plus y dot x dash plus z dot y plus z, right? This is given, and then so the first step is basically applying the distributive property. Applying the distributive property. Okay, so yz x plus y dot x dash plus z. So if I apply the step 1, if you look at in problem number 4, you brought x there in the last term. So let us bring x dash like this, y plus z. Right? So that will give you x plus y dot x dash plus z dot, then you have x plus y plus z dot x dash plus y plus z, right?
Yes, sir.
You get that. So that is step 1, if you go by the duality of whatever is shown there. Now the next step is basically grouping. So what you need to do is basically group. There is x plus y here, x plus y here, and there is another group you can do is this one. So let us do that grouping. So x plus y, so x plus y you can treat it as x plus y dot 1, and this is x plus y plus, or x plus y not dot 1, plus 0. You treat it as plus 0. So x plus y plus y plus 0 dot z. Okay, so I am trying to combine these two terms. So it will be x plus y plus 0 dot x plus y plus z. You see that?
Yes, sir.
And similarly I can combine these two terms also. So this I will put a bigger bracket, and then so here if I write in a similar manner, I will write x dash plus z plus 0 dot y, x dash plus z plus 0 dot y. So x dash plus z plus 0, that is this term, dot x dash plus z plus y, that is this term. Clear? That
Yes,
is
sir.
the next step. Alright, so now this is what? 0 dot z and 0 dot y, that is 0, and 0 plus anything is that thing. You get it?
Yes, sir.
Yeah. So
Thank you, sir.
yeah. So that's how we can use the properties of the Boolean algebra to do these manipulations and change the form.